Hello, everybody. In this lecture series, I will provide an introduction to systems engineering. This course is about systems and systems thinking. Let's start with one simple example. An airplane. Any organization who design an airplanes, it has several teams or groups. Some common are the fuselage or the main body, the aerodynamics group or team, the weight, wings, hydraulics, stress, control, stability, and so on. We also have other groups like the environmental groups, the legal, the social, financial, management, and many other teams involved in designing an airplane. Now, I want you to think for a moment what would happen if only one of these groups gets all their own way, has the power because they think their groups is the most important one. Of course, the fuselage team, they thinks that they need to get the maximum space for the luggage, for the passengers. So they may came up with this design. This is an ideal design for the fuselage group. But the aerodynamics groups disagree. They want their systems or their airplanes to have the best aerodynamics performance. And of course, with their plane, you hardly can fit anybody there. And the weight groups, they want to have the lightest possible airplane. Perhaps they convince you that the best airplane is the one that made out of wood. And the wing groups and the stress group have their own way, as you see, and it's illustrated in these pictures. This is actually a cartoon that I adapted to this topic. Now I want you, as this picture shows, that each teams or each groups, they think they are the most important and their function is the most important. But here the systems engineers come to guide these groups. And what it does, it tells you that we're not looking for the best, because the best, we are going to end up with satisfying one aspect of the systems, but sacrificing many aspects of it. And our system is not going to be successful. So what the systems engineers is looking is not for the best, is looking for good enough. It looks at the big picture and try to balance different requirements. So you may think then it's like solving a Rubik cube, right? Most likely you've tried it before. You try to perhaps get one phase correct. Maybe you almost got there, but you messed up with the rest of it, right? Now, I want you to think about each phase of this Rubik cube as one aspect of a system. Maybe the performance, the cost, safety, and the environment. Systems engineering has to have some strategy to solve these puzzles, to satisfy all these aspects of a system. Now let's get a little bit formal about systems engineering. A definition of a systems engineering is guiding or providing the guidance for the engineering and development of complex systems. So they look at the system as a whole, right? I want you to focus on a few things here. We emphasize on complex systems. So the system that we're going to be concerned about are complex systems, the one that has several subsystems from different disciplines. For example, a bicycle can be considered as a system, but it's not something that we consider it as a systems engineering for analysis because it's not complex enough. It only involves mechanical engineering. But an airplane, which involves mechanical, electrical, computer, environmental, fluid dynamics, aerodynamics, many aspects is a system, considered a systems engineering. So the key concepts are it has to be interdisciplinary approach with systems engineering. As I showed you in the example of airplane, we try to balance the performance, the cost, and the schedule. And we emphasize on the needs and the life cycle of the actually the product as a whole. What are the characteristics of a system? As I mentioned earlier, a system is a bunch of components that they are interrelated, working together toward a common goal. What considered to be a complex systems, it has to be diverse, intricate relationships between components, and it should be engineered. For example, the organism, my body organisms, or ecosystems, they are systems, but they are not something that we analyze them under the engineering, under systems engineering. Good examples, an aircraft, a satellite, a global network, they are all under the category of systems engineering. But your washing machine, your bicycle, mechanical pencils, we will say they are not complex enough to be considered as something to be analyzed under systems engineering. Here are some examples. Material and energy systems, for example, an aircraft, and oil refineries, sawmills, and they're all can be considered as systems engineering or systems that require systems engineering. They don't have to be materials or energy. They can be, for example, signal and data system. For example, the weather satellites or the airline reservation systems. They all can be considered as systems. A little bit of history. End of World War II, they feel the need for a different approach. Maybe it comes from the pressure of the scheduling and satisfying many aspects of the wartime. And then slowly with the advance of jet engine development, the radar, the digital computings, the needs of systems engineering becomes felt more and more. Perhaps because the systems become more complex, also the automation and digitalization came to play, and cybersecurity became a concern. And that's where the needs for system engineering emerged. Uh, what is the viewpoint of a systems engineering? A good system, or we call it a total systems, first of all, meets the requirement objectives and it operates over its life cycle successfully. So we need to consider from the design until the retirement of systems, all aspects of it. We have to balance the conflicts of the best of each subsystems. Think about again that airplane examples that I provided for you earlier. You need to balance many aspects of it, the performance, the cost, the schedule, and many things. And of course, you need to have a viewpoint of or interdisciplinary integration viewpoint to encompass different aspects of each subsystems. You need to switch your mindset to system thinking. And it means you need to have a holistic view to a systems. In other words, you need to focus on the big picture, right? And you need to think how this big picture can satisfy the requirement of many aspects of the systems. And of course, it consider a broad perspective, considering the technical, management, and social domains for each system. There are different methodologies in systems thinking, and some common of these are the linear, waterfall, spiral, and V approach. In today's lecture, I'm not going to go to the focus of these, but in future lecture, we'll focus more on each. Just a brief introduction. The linear methodology, it's more applicable to when we have, let's say, a technology available, there is an opportunity out there, and based on that opportunity, we want to develop let's say, a new system. So it's linear, as the name implies. You start with the concept development, you develop it, and then after development, you think about its life cycle and so on. Another approach or methodology is the waterfall. It's more applicable when you have already a system, let's say a car, and now you want to develop new systems with new requirements, maybe some upgrade to that. You start with some basic requirements, and then based on those requirements, you define functions. And for each function, you try to design a physical component, and then you integrate all of them to a design, then you validate it. Again, in future lecture, I will get to that in more details. The spiral models is an interesting one. It starts with need, and then similar to the other models, the waterfall. So you analyze the need, and then you check the requirements and do the functional analysis. You decompose the system to subsystems and to sub-functions, and then try to come up with solutions. And as the name implies, is go in a spiral until you reach your goal. We'll get to more details of these in future lectures. And lastly, the V model. This is the most common, and it has very similarities to other models. Again, you start with the requirements, and you go all the way to the retirements and recycling perhaps of your system. And there are different aspects that you will consider and analyze it, which we will go to more details of this model as we move forward throughout the course. Since this is our introduction lecture, I'm just going to briefly provide a little bit of background. If this is a good profession for you, is this something that you should consider as a career? First of all, systems engineering, I should emphasize, cannot be taught. It's something that you need to earn it through experience. But there is a formula. How can I become a systems engineer, which I'll briefly provide it for you. But is it a good career? Yes, it is. There is an increased demand in government and industries, of course, with the advancing technology, with the complexity of systems, with the cybersecurity, the need is more and more. Unfortunately, currently there is not so many universities who offer this as a degree. It means industry, for industry, there is not so many people when they advertise a job who apply for the job. And there are all these senior actually engineers who have this long experience that can apply for this job. And I believe it's highly unlikely that it be automated. One of those jobs that most likely is going to be for a long time. So it's a good investment. Now, the question is, what quality should I have? You need to be good in problem solving, good to have knowledge in different aspects of technical knowledge, in different aspects of a project. For example, if you start as a base as a mechanical engineer, but you need to know a little bit of electrical, a little bit of computers, and so on, and you need to gain that knowledge through experience again. You cannot just go and read few books for each topic and claim that you learn that topics. And of course, you need to have a good communication and leadership skills. This is an image which I got it from the book, The Art and Science of Systems Engineering from NASA. It's a good book. It's not a book, it's an article. I recommend reading that one. You may pause the video and look at the different characteristics of somebody who perhaps or potentially become a good systems engineer. And of course, there are different aspects. What I like to emphasize, you need to be somebody who comfortable with change and comfortable with uncertainty. if you are one of those engineers or people that you need to know everything in advance, maybe this is not a good career for you. You need to be able to deal with uncertainty, with sudden change of direction in running a project. A little bit of paranoia and being dubious about everything and every solution, but again, in a good way. We'll discuss it more later. And of course, being decisive. If you are one of those people who cannot make up your mind when it comes to making a big decision, maybe this is not a good career for you as well. You need to make a decision, of course, considering different aspects of it, but being decisive and not being afraid of making a decision. This is a T model, which sort of, but not necessarily, tells you how I can become a systems engineer. Well, you need to start earning a degree in one of the major traditional engineering, in civil, mechanical, electrical, aerospace, or applied mathematics. That's your base. That's the foundation. Then you start a job, you join a company, let's say a big firm or organization like an airplane or car manufacturer. Uh, you gain technical experience after 4 or 5 years, then maybe you move up to the ladder and you become a project lead for small projects. Then slowly you grow up until after maybe 15, 20 years, and perhaps along the way you read some books related to systems engineering, maybe get a master's or a PhD, and this is where you are ready perhaps to become a systems engineer. As you can see, you started with one degree, but along the way, slowly you expand your knowledge in different areas, particularly applicable to that project or that organization that you are working with. So it's a long journey, but if you have good curiosity, solving challenging problems, you love leadership, and you are good in communication, you are okay with uncertainty, you like to make big impacts in big organizations, um, and you like to work with big systems. Some people, maybe they wish to focus on designing something small and smart, which is perfect for them. But some people like to deal with big systems. Maybe this is a job for you, and this is one way. Of course, this is not the only way. But again, as I emphasized earlier, this is one of those topics that cannot be taught. I'm going to have a series of lectures, but at the end of the lectures, I cannot claim that I teach you systems engineering, but I gave you enough material that you are familiar with the terminologies and you can continue on your own, read, and when you join or work in a company and in a firm, then you understand their vocabularies and you aim toward that systems engineering career. I want you to pause for a moment and think about a symphony or orchestrate, musical orchestrate as systems. Who is the systems engineer in this picture? Well, perhaps you guess the conductor, right? The orchestrate conductor is the systems engineer. So now think about this conductor. He needs to be master in one or two instruments, not in all instruments. And he needs to know a little bit about each other instruments. And of course, if he's a composer, a musical composer, that would be best. And he needs to compose few maybe music. Beside that, he needs to know the general aspects of a good music, the rhythm, the dynamics, and the frequencies, and many other aspects of it. And of course, many years of experience, then he can become a successful conductor. At the same time that he manage these groups, he needs to have a good feedback, get a good feedback from the audience, feels them, their emotions, their excitements, so he can adjust the timing, he can change the rhythm and the dynamics of the teams. So think about the systems, successful systems engineer as a good musical conductor or orchestrate conductors. Let's summarize. We talk a little bit about definition and scope of systems engineering. In general, we say the systems engineering guides development, engineering and development of complex systems. A systems engineer have to balance the performance, cost, and schedule. We talk about key concepts, systems thinking about having a holistic view about systems, the life cycle approach, and also the interdisciplinary integrations. The future trends, increased automation, of course, the complexity of the system is increasing, the security, cybersecurity, it also provides good or future job opportunities for systems engineering if you consider it as a profession. Now, I want you to reflect for a moment and perhaps think about now how does systems engineering, based on what we discussed, differ from the traditional engineering disciplines like the mechanical, electrical, computer, civil, or aerospace engineering. Also, down below, I'm gonna provide a couple of examples of complex systems for you. And I want you to think about other systems. And please add your examples below so other people, they can read them and perhaps come up with their own ideas. With that, I'm going to say goodbye. And in future lecture, we are going to delve more into systems engineering and systems thinking. Have a great day. Goodbye.